Okay, so in this video we'll be talking about the modulus of complex numbers. Okay, so what is the modulus of complex numbers? Well, let's back up a little bit. When we talked about vectors, we talked about vectors having a magnitude and direction, right? Well, complex numbers, when they're talked about in terms of vectors, also have a magnitude and direction. Okay, we said in the Cartesian form, complex numbers look like this. In the vector form, they look like this. And so the magnitude of that vector is basically the modulus of that complex number, or of that vector. Okay, and we find the magnitude just like we do vectors by taking the square of each component, adding them together, then square rooting them. And that is basically the Pythagorean theorem, isn't it? So that's the modulus. The modulus is just the magnitude of a complex number. Okay, and we also talk about something called the argument of a complex number, which tells me the direction that it's going in, also known as the angle, but we'll be looking at this in a later video. For now, we'll focus on the modulus. Okay, so how do we find the modulus? Well, we just use this formula right here, okay? It's just the Pythagorean theorem. It's just this right here to find the length of the vector. So if I have z equals minus 3 plus 2i, I take each of those components, square them, take the square root of the whole thing, and of course add those squares up, and we get root 13 in this case. Okay, so very straightforward, just like we do with vectors. Okay, now there are some properties of the modulus that you need to be aware of, and these are very, very important for doing certain problems involving complex numbers. Please keep in mind that these are not the same as the properties of the conjugate of complex numbers. Okay, so we're talking about the modulus here. Okay, different from complex conjugate properties. Okay, so you do need to get enough practice to make sure that you can distinguish between these two, because it does get a little bit confusing later on. All right, so the modulus of z star is the same as the modulus of z, and that makes sense. The length of each of these vectors, because they're mirror reflections of each other, they will stay the same. The modulus will be the same. Okay, this is a very key one that you're going to need to know. The modulus of z squared is the same as z times z star. Okay. This will make a lot more sense probably as you do your homework. I think you will actually be verifying this, okay? But this one is a very key one that we'll use to do some solving for modulus z type problems. The modulus of z1 times z2, where we have two complex numbers, is the modulus of is the product of each of those complex numbers modulused first, I guess. I don't even know if that's a word, but you take the modulus of each of those and each of those numbers and multiply them together. Same thing with the product, the quotient. You can think of this as the modulus symbol kind of distributes across, just like the conjugate symbol distributes across. Okay, note that this doesn't work necessarily for addition and subtraction, but just for multiplication and division here. Okay, and if I have the product of many different complex numbers and then I find the magnitude of all of those, it's the same as finding the magnitude of each of the individual complex numbers and multiplying those magnitudes together. Also, z to the nth power, when I take the modulus of that number, it's the same as finding that number, finding the modulus of it, the magnitude of it, and then raising it to the nth power. Okay, and notice that n is always going to be a positive integer. So if this is 0 or negative, if it's a fraction 1 over z, this property would not work. Okay, let's do one example here. It says prove that this is one of our properties. We're proving that z1, z2, the modulus of that, is equal to the modulus of z1 times the modulus of z2. Okay? Show that this is true for all z1 and z2 complex numbers. Okay? So we start just like we do with proving or verifying some of our complex conjugate properties. We're going to say let z1 equal a plus bi, z2 equals c plus di, okay, di, and we're going to start with the left side and make it look like the right side. So just to kind of think about some intermediate steps here, this side would have to look like this, right? This would the modulus of z1 would be the square root of a squared plus b squared. z2's modulus would look like this, okay? So what we do is we take z1, z2, and let's just figure out the inside part first. So I'm going to multiply z1 and z2 together in terms of their components. So I have a plus bi times c plus di. If I expand everything out and simplify it again, I can break it into one real part, one imaginary part, and it would look like this. Okay, this still has a modulus symbol around it. Now that this is one number, okay, this is one complex number, I can now find the magnitude of this one number. So it takes a little bit of algebra, but I can take the square root of that. Sorry, the square root of the real part squared plus the imaginary part squared. Okay, and that's what I'm doing here. Once I have that, I expand everything, and these terms would cancel. I can now regroup the remaining terms. Okay, remember my goal is to get it to look like this, right? I need to have these two multiplied together, so maybe I need to have this and this quantity, these two quantities under the same square root. And that's what we're going to do. So I need to factor out my a squareds from these two and my b squareds from these two, and what I'm left with is c squared plus d squared in each as a separate factor of each of these. So I have a squared times c squared plus d squared, b squared times c squared plus d squared, and then I can factor one more time. So I'm factoring out two times. Okay, and so then we get the right hand side. All right, so that would be the proof of this property here.